I would like to talk to you about one of the applications of quantum theory, the application to magnetic monopoles. I will tell you first about the theoretical ideas which led one to think of monopoles, and then I shall tell you about the recent experimental claims to have discovered a monopole. One works from the idea of the Schrödinger wave function. One does not need to have relativistic ideas for this argument. One just can discuss it from the point of view of three-dimensional space. One has a wave function psi, which is a function of the three coordinates, x1, x2, x3, and may also vary with the time. And then one knows that the usual interpretation of that wave function is that if it is normalized, the square of its modulus gives us the probability of the electron being in any particular place. Now, this psi is usually a complex number. We are able to multiply it by a phase factor. A phase factor is a number of the form e to the I gamma, where gamma is a real number. E to the I gamma is a number of modulus unity. We may multiply psi by e to the I gamma, and then we get another psi having the same mod psi squared, so it corresponds to the same probability distribution. Let us multiply it by e to the I gamma and call the new one big psi. Big psi and little psi correspond to the same probability distribution. Now, gamma there doesn't have to be just a number. It could be a function of position in space, or even in space-time. We may take this gamma, therefore, to be a function of the three x's, and probably also of t, and then we still have a new psi with the same probability distribution. However, this new psi and the original psi will no longer satisfy the same wave equation. If we form the big psi by the xr, r being a suffix that takes on the values 1, 2, or 3, this will equal e to the I gamma d by the xr plus I kappa r times psi, where this kappa r is a function of position. Kappa r equals d gamma by the xr. If we have big psi satisfying some wave equation involving the d by the x's, little psi will satisfy the corresponding wave equation with d by the xr plus I kappa r instead of the d by the xr. Now let us go one stage further. Let us suppose that this kappa, let us suppose that gamma becomes what mathematicians call a non-integrable function. That is to say, we must imagine that gamma does not have a definite numerical value at any point, but it still has a definite change in value when one goes from one point to a neighboring point. Gamma is now something without a definite value at a particular point, but it has a definite change associated with a passage from one point to a neighboring point. Now we may continue to move our point and go around a closed loop. And with this motion, gamma will be continually changing, but as a result of all these changes, it may end up with a different value from what it started with. The value of gamma may change when we go around a closed loop, and for that reason gamma does not have a specified value at each point. Let us introduce such a gamma into this phase factor here. The result will be that we shall still have an equation of this type, but kappa r will now refer to the change in gamma when we go from one point to a neighboring point, and this change will no longer be the gradient of a scalar. This formula will have to be cut out. We have to consider kappa r as something more general, and this kappa r will be something such that when we take kappa r dxr, integrate it around a closed loop, the result need not be zero. If we do that, we get a physical theory which is definitely more general than what we had before, but it is not essentially new because it is very similar to the physical equation which we have for an electron in an electromagnetic field. You know that if you have a theory of an electron in the absence of any field, could be either classical Hamiltonian theory or quantum theory, you introduce a field by taking the momentum variables PR in the absence of a field and replacing PR by PR plus E over C AR, AR being the potential. If this big psi satisfies the wave equation in the absence of any field, little psi will satisfy the corresponding equation in which PR is replaced by PR plus E over C AR, and PR is minus IH d by dxr in the Schrödinger theory, and this has to be replaced by minus IH d by dxr plus minus I EH over C AR. This is the passage, this is the change in the wave equation which corresponds to the introduction of the electromagnetic potential AR. And you see that this change is the same as the change introduced by the non-integrable phase factor if we just identify this term here with this one. That is to say, we have to identify kappa R with EH over C AR. What that means is that introducing a non-integrable phase is the same thing as introducing electromagnetic potentials. The potentials being connected with the non-integrability of the phase by this equation here. That gives us a new picture for the electromagnetic potentials. It doesn't give us at this stage any new theory, any new physical theoretical theory. It's just a new mathematical picture for the equations which we have, just a new mathematical picture for the Schrödinger equation in which there are potentials acting on the electron. Let us consider the total change in the phase, that is to say, the total change in gamma when we go around a closed loop. Change in gamma around a closed loop is the integral kappa r dxr integrated around the loop. Now we are to identify kappa r with E over c AR, so we have EH over c integral AR dxr. Let us now use Stokes' theorem, which enables us to express any integral taken around a loop as a surface integral taken over the surface which has this loop for its perimeter. We get EH over C integral curl A. This is a vector. We want the scalar product of this vector with an element of the surface ds. ds is also to be considered as a vector in three-dimensional space. And we get EH over C times the integral of H ds. H being the magnetic field. So we have this numerical factor multiplied into the magnetic flux going through the surface, which has this loop for its perimeter. That is the result of this calculation. The total change in gamma when we go around a loop is connected with the magnetic flux which is going through the loop. Now we have to bring in a new factor. We have to take into account that gamma, appearing as a phase like that in the wave function, is undetermined to the extent that we can add to it any integral multiple of 2 pi. Replace gamma by gamma plus 2 pi, and it doesn't affect that top equation there at all. And if we take this equation, which we deduced here, we see that the left-hand side is really undetermined to the extent that we can add to it any integral multiple of 2 pi. So that the equation can't be a complete and definite equation as it stands if the left-hand side is undetermined and the right-hand side is completely definite. With this picture for interpreting the electromagnetic potentials in terms of a non-integrable phase, we have to generalize that equation and say that change in gamma plus 2 pi n, n being any integer, positive or negative, is equal to magnetic flux multiplied by this numerical factor EH over C. So that if we take any closed loop, the change in gamma when we go around that closed loop plus an unknown multiple of 2 pi is EH over C times the magnetic flux going through the loop. Let us now bring in conditions of continuity. Well, before going on to that, there's one further point I should make, that I've been considering here just one particular wave function, but we must have the same non-integrable phase factor associated with all the wave functions in order that superposition relations between the wave functions can be maintained. We can add 2 wave functions and get another one. Well, if we're going to multiply one of our wave functions by a phase factor into the I gamma, we must multiply them all by the same factor in order that the superposition relations will not be disturbed. Now let us go back to this equation and apply considerations of continuity. Let us take a small loop. For a small loop, the change in gamma, when we go around it, will be small, because the change in gamma is always small, and so it can't change very much going around a small loop. Similarly, the magnetic flux through a small loop will be small under normal physical conditions. N has to be an integer, and if these two numbers are both small, it means that n has to be 0. So conditions of continuity will usually tell us that n has to be 0. There is, however, an exceptional case. I said the change in gamma going around a small loop has to be small, but that is not true under certain conditions. If psi is 0, then gamma is completely undetermined. If psi is close to 0, then small changes in psi may correspond to quite an appreciable change in gamma. Just take the example of psi equal to x1 plus I x2. There's a psi which is 0 when x1 and x2 are both 0. This psi is perfectly continuous in the neighborhood of x1, x2 being 0, but the change in the phase of this psi is 2 pi when we make a passage around a small loop enclosing the origin x1 equals x2 equals 0. So we have to consider those regions where psi vanishes. If psi vanishes, that involves 2 conditions, and in 3-dimensional space those 2 conditions will usually be satisfied along a line. We call that a nodal line. There are nodal lines where psi vanishes, and if we take a small loop around a nodal line, the change in psi when we go around that small loop doesn't have to be small. It can be 2 pi or any multiple of 2 pi, even though psi is perfectly continuous. That is shown by this example here. We can infer that n is 0 for a small loop except when the loop encircles a nodal line. If we now go over to large loops and apply this formalism to a large loop, we see that the magnetic flux passing through the large loop multiplied by EH over C will equal the change in gamma going around that large loop plus a contribution of the form 2 pi n coming from each nodal line that passes through that large loop. This large loop will enclose some surface, and there is a contribution of the form 2 pi n for each nodal line that cuts through the surface. Now, let us apply the formula to a closed surface. A closed surface has no boundary perimeter at all. If we apply this formula to a closed surface, change in gamma going around the perimeter is 0 because the perimeter itself has shrunk up to 0. We have 0 there. We get the result that EH over C times the magnetic flux crossing the closed surface is 2 pi n. Well, it will be the sum of terms 2 pi n, one such term for each nodal line that passes through the closed surface. If we have a nodal line coming from infinity, cutting through the surface, going inside the surface and out again, that nodal line will make two contributions which will just cancel each other. We get a non-zero total only when we have one or more nodal lines which end inside the closed surface. So we are led to consider this situation. We have wave functions which involve a nodal line that has an end to it. The end will be some sort of singularity. We don't need to discuss it in detail. The end of the nodal line will be some singularity in the field. We take a closed surface surrounding this singularity, and then the total magnetic flux going through this closed surface will be 2 pi n, there being a definite n associated with this nodal line. Now, if we have magnetic flux crossing a closed surface, it means that there is some magnetic monopole inside the surface. And the strength of the monopole, if we call it mu, will be such that 4 pi mu equals the flux, the magnetic flux. That formula is perhaps a little unfamiliar, but if you think of the corresponding formula for the electric field and the electric flux, you see that it is immediately familiar. 4 pi times the electric charge at a point is equal to the electric flux crossing any surface, any closed surface surrounding the point. Well, that's just the elementary formula of electrostatics transferred to magnetostatics. We have 4 pi mu times the magnetic flux we have 4 pi mu equals the magnetic flux. And if you compare these two equations, you get a formula for mu. Mu equals EH over 2c times n. We've got a formula for the strength of the magnetic monopole. This formula comes out quite definitely from these quantum considerations, and there's no escape from it if you're going to have magnetic monopoles occurring in the quantum theory. Putting it more directly, one can say that in order that we may have an electron moving in the field of a monopole, in accordance with Schrödinger equation, that monopole must have a strength given by this formula. Otherwise, the equations are not consistent. This is demanded by the Schrödinger formalism. We may use the experimental result that E squared over hc equals the other way around. Hc over E squared equals 137. I've got this up the wrong way around. U equals hc over 2e times n. I've got the h in the wrong place here. Using this numerical relationship, we get 137 over 2 En. You see, if you take the smallest value for n, 1, you get for the strength of the pole something which is much greater than the charge of the electron. 137 over 2 times is large. This minimum monopole is thus quite a large thing. Now, this theory just shows that such monopoles can exist consistently with the Schrödinger equation. There's nothing to say that these monopoles have to exist. Whether they exist or not is something which can only be decided by experiment. There is one argument which would be in favor of the existence of these monopoles. Namely, they would provide an explanation for why electric charge is always quantized. For all the particles which are observed in nature, the electric charge is always an integral multiple, positive or negative, of the charge on the electron E. Now, why should that be so? Why shouldn't there be quite different values for the charge occurring on certain particles? There is no theoretical explanation for that, except for this theory of monopoles. If there exists one monopole anywhere, then in order that a charged particle can interact with this monopole, in order that we can set up a wave equation for the interaction of this charged particle and the monopole, which should be consistent, it is necessary that the charge on that particle and the strength of the monopole should be connected by this relationship here. So if there exists exists a monopole anywhere, it will be necessary for all the charged particles in nature to have their charge quantized. It will be a satisfactory thing because it would help to explain a feature of nature for which there is no other explanation known. However, that's not sufficient to prove that monopoles must exist. Let us examine a little how a monopole would appear experimentally. If we have a monopole sitting on a particle here, then it is quite stable. There is a conservation of pole strength, just like the conservation of electric charge. The Maxwell equations are symmetrical between electric and magnetic fields, and the Maxwell equations demand conservation of electric charge, and they would similarly demand the conservation of pole strength. This particle, which has a monopole sitting on it, might perhaps not be a stable particle, but if it disintegrates, there must be some monopole among the products of disintegration. The monopole itself is something which is quite permanent and cannot disappear. Once you have a monopole here, the only way in which you could make it disappear would be to have another monopole of equal size and opposite sign, and have the two interacting with each other. And then they may annihilate each other with the energy going off into some different form. One monopole by itself is perfectly stable, and only two monopoles of opposite sign can disintegrate each other. Now, if we are going to make monopoles with some high energy atomic apparatus, you have to make them in pairs, one positive and one negative. You have to make them both simultaneously. People have searched for monopoles with the high energy machines, and they haven't found any. That is not a proof that the monopoles don't exist, because it could very well be that simply the energy of the monopoles, the rest energy of the monopoles, is too large for a pair to be created with the existing machines. You might expect the rest energy to be rather large, because the monopole strength is large, much larger than the charge on the electron. And that's therefore not a surprising result that monopoles have never been detected in a high energy apparatus. One might hope to detect them among the cosmic rays. The cosmic rays coming in from outer space have energies enormously greater than any energies which can be created in the laboratory. And it could be that there exist monopoles among the cosmic rays, and people have been searching for them. They've been searching for them for some decades, and it is only recently that claims have been made to have discovered one of them. How would a monopole appear experimentally? Well, one must ask what sort of ionization it will produce if we have a monopole passing with high velocity through matter. Let us compare the ionization trail of a monopole with the ionization trail of a charged particle. Here we have a charged particle, and we have matter around it. Take an atom here. this charged particle will disturb the electrons of the atom and may pull out some electrons and produce ionization. The electric force which is pulling the electrons out will be proportional to the charge of this particle. The time during which that force acts will be inversely proportional to the velocity of the particle. That's called v. Let's call the velocity v. And then the impulse which the charged particle passing by gives to one of these electrons will be proportional to E over V. That means to say that the faster the particle moves, the slower the less the impulse will be. It will tend to E over C for the particle moving with a speed close to the velocity of light. As this particle loses energy and gets towards the end of its trail, the ionization increases because V gets smaller, so that we shall have an ionization track which gets bigger as the charged particle goes towards the end of its path. The electric field produced by the monopole is proportional to the velocity of the monopole. That corresponds to the well-known result that the magnetic field produced by a moving charge is proportional to the velocity of the moving charge. So that with a monopole going by, we have a force proportional to the velocity of the monopole. The impulse which the monopole gives to one of the electrons here will thus be the force proportional to the velocity multiplied by 1 over the velocity. It will be pretty well independent of the velocity. So that a monopole going by here will produce a trail of ionization which is pretty steady and does not increase towards the end of the trail. That is a way of distinguishing a monopole from an ordinary charged particle. And that is the method which was used by Price and others for their recent experimental work, which led them to believe that they discovered a monopole. What they did was to send up some recording apparatus in a balloon and keep it near the top of the atmosphere for a few days, and then bring down their apparatus and analyze it. The apparatus consisted mainly of a pile of Lexan sheets, which is a certain kind of transparent material. There was a whole set of these sheets, one on top of the other, and any ionizing particle passing through these sheets damages them in a certain way, and the amount of the damage can be assessed by etching the sheets. The sheets were all etched. We examined the etch marks to see how much ionization there was. I would like to give a diagram to show the results that they obtained. Notice there's a gap at the top between the first of these Lexan sheets and the remaining ones, and in that gap there was some other apparatus. There was a Cherenkov counter and also an ordinary emulsion plate. As a result of the observations of this emulsion plate, they were able to infer that the particle was moving downwards just from the delta rays. And with the Cherenkov counter, they had some information about the velocity of the particle. This is the gap, and then this is the whole stack of Lexan plates. And these dots and triangles indicate the amount of ionization in these plates. The circles and the triangles differ only through having different times of exposure to the acid which is causing the etching. And you see that these sheets, these points, do lie pretty approximately along a vertical line, indicating that the amount of ionization is fairly constant. If there was a charged particle instead of a monopole producing this ionization, the curve should go towards the left here, because it should go towards the right here, because the ionization should increase towards the end of the trail. And this dotted curve here is what you'd get with a charge of about 96 and velocity 3/4 of the velocity of light. And you see that this sloping curve doesn't fit the data at all. The vertical curve does fit fairly well, even though there are quite a lot of discrepancies, experimental errors. It is that figure which supplies the basis for the claim of Price and his co-workers that it was a magnetic monopole which they had caught in their apparatus. I was discussing this work with the physicists in Sydney, and someone in Sydney said that one possible cause of error would be that maybe there is some saturation phenomenon coming in with the etching process, and that even if the plate is very heavily damaged by ionization, there will not be a corresponding increase in the size of the etch mark owing to some saturation effect. That was a possible criticism, and I don't know to what extent it is valid. It seems this was only a preliminary report that has been issued, and of course that is something which would have to be looked into very carefully to see that the size of the etch mark does really correspond to the amount of ionization which the particle is producing. Professor George in Sydney was sufficiently interested to ring up Alvarez in Berkeley. Alvarez is the head of the laboratory where this work was done, and ask Alvarez what was his opinion about it. And Alvarez was very hostile to the interpretation of Price and the others. Alvarez said it could be that you had some charged particle producing the etchings up to this point, and that at this point the charged particle hit some nucleus and underwent a disintegration, as a result of which it continued with a reduced charge. On the basis of his telephone conversation with Alvarez, the physicists in Sydney have constructed another diagram which I'd like to show you. They suppose that you start off with a charged particle, Z equals 96 they took, which continued up to this point and then hit an atomic nucleus, underwent a disintegration, and then there was a reduced charge continuing down here. Maybe this new particle was unstable and perhaps emitted an alpha particle and underwent a further transformation here. It could be that this would provide an explanation alternative to the monopole explanation. That is a question which hasn't been decided. In any case, even if Alvarez is right, it will be a sort of a coincidence that the overall picture is very closely vertical. It would seem that nature has rather been trying to deceive you. I don't know what the real answer is, and we have to wait for the experimental physicists to study these results in greater detail and come to some conclusion. Professor Hoare in Sydney rang up Hofstadter to ask him what his opinion was. Hofstadter was rather uncommittal, and he said he thought it was 50-50. Either Price is right or that Alvarez is right. I think that that's perhaps my opinion also. We have to leave the question open for the time being. There's one observation which rather speaks against the interpretation of these results in terms of a monopole. If monopoles are coming in the cosmic rays, presumably lots of them have arrived in the past, and they will come down through the atmosphere, and they will stop somewhere or other. We ought to be able to find them. One monopole by itself is perfectly stable, and if the total number of monopoles is rather small, the chance of one monopole meeting another monopole of the opposite sign is very small, so that they don't have much chance to annihilate each other. And if there are these monopoles coming in the cosmic rays, you would expect to have a lot of them lying around. People have searched for them in many places, all the places they can think of, and they haven't found any yet. They would probably tend to go towards the poles of the Earth's magnetic field. And people have made their searches at regions of high latitude for that reason. But still they haven't found any results. It may be that the monopoles are sinking to the Earth in the hopes of getting close to the Earth's poles. It could be that they just haven't been found because they penetrate too far into the Earth's surface. We don't really know how well they would penetrate through solid matter. I don't think anyone has estimated that, and it would be pretty difficult to estimate without knowing more about the monopoles. Price and the other workers believe that their monopole has a mass of about 200 proton masses, or could be larger. Of course, with that mass, it would be explained why they are not observed with the high-energy machines. The high-energy machines will not have enough energy to create a pair of particles with this mass, which would need simply an enormous energy in the rest energy frame of the collision process. I think I must conclude at this point and leave it as a question for you to puzzle over whether these monopoles exist or not, and hope that the experimentalists will come to something more definite. Price and the other workers have promised another paper. This one was published in the Physical Review Letters of August the 25th. They have promised another paper to appear shortly, in which they will answer the problems raised by this criticism. I will stop there.